Hello everyone, and welcome to this advanced lecture on discrete phase modeling, that is DPM. In this lecture, we will study how to conduct discrete phase modeling within the commercial software Fluent. This particular lecture is part of the advanced lecture series on multi-phase flow modeling brought to you by Center for Computational Technologies. Before beginning this lecture, let us have an overview of what we will study in this lecture. First, we will have an overview of the fundamentals of discrete phase modeling. We have already studied a lot of fundamentals and basic concepts related to discrete phase modeling in our earlier lectures. So we will review all those concepts and basic fundamentals just to prepare a solid base before we go into studying discrete phase modeling in detail. After that, we will see how to set up the discrete phase model within the commercial software Fluent. We will see each and every step involved one by one. In the next section, we will study all the user inputs that are required to set up the discrete phase model. We will discuss in detail all the parameters related to discrete phase model and all the inputs we have to give in order to set up the discrete phase model. Then we will end with the summary of this particular lecture and we will see the references before we end. So let us begin the first section, which is review of the discrete phase model. This will cover the basic concepts and fundamentals of the discrete phase model. So basic principle that is behind the discrete phase model is the Eulerian-Lagrangian framework or the Eulerian-Lagrangian approach. In the Eulerian-Lagrangian approach, Eulerian framework is used for the continuous phase, whereas Lagrangian tracking is used for the dispersed phase. Which means continuous phase is modeled using the Eulerian method, whereas only equations of motions are solved for the dispersed phase. Equations of motions are solved by tracking or the Lagrangian method. This particular approach is ideally suitable for very low volume loading or when the volume fraction of the secondary or the dispersed phase is very small. What we must note or keep in our mind is that in this particular approach, volume displacement due to the dispersed phase is ignored. That is, when there is dispersed phase in the form of either particles or droplets, it occupies some volume of the continuous phase or it displaces some volume of the continuous phase, which is equal to the volume of the dispersed phase. But this volume displacement is ignored in the discrete phase model or discrete phase approach because volume loading of the dispersed phase is very low. So it does not affect the modeling accuracy if we neglect this particular volume loading of the discrete phase. So this is a pictorial representation of the Eulerian-Lagrangian approach, which is the basic behind the discrete phase model. In the Eulerian-Lagrangian approach, as you can see, continuous phase is indicated by blue continuum and there are discrete secondary phase particles shown here. All these are the discrete phase particles. Now, the trajectory of these discrete phase particles is calculated by equation of motion. That is, governing equations are not solved, but just the equation of motion, that is Newton's law of motion, is solved for these particular discrete phase particles. Whereas for this bluish continuum zone or continuous medium, Eulerian framework governing equations are solved. That is, Navier-Stokes equation are solved for this continuous phase. Now there is coupling in between this discrete phase particle and the continuous phase in the form of drag or lift, heat exchange, mass exchange, etc. So this particular coupling or exchange is modeled using various empirical equations or models. Now let us review the flow governing equations that are solved for continuous and the dispersed phase within the discrete phase model or the Eulerian-Lagrangian approach. First we see the continuity equation. This is nothing but the part of the Navier-Stokes equation, continuity equation. Here alpha is volume fraction of the continuous phase and this is how the continuity equation for the continuous phase is solved. Sc is the mass source term. Momentum equation is also solved for the continuous phase. It's the standard Navier-Stokes equation. Again, alpha is the volume fraction here. These are the transient or unsteady momentum and continuity equations. Now for the dispersed phase, trajectories are calculated using equation of motion. Equation of motion is nothing but Newton's law of motion, and this is used for each single dispersed particle. Newton's law of motion is used for each single dispersed particle and the force balance is calculated. This is nothing but an expression which says that mass into acceleration is force. So here all different forces which arise by interaction of the dispersed phase with the primary or the continuous phase are included. Fd is the drag force, Fp is the pressure force, Fvm is the virtual mass force, and Fg is the body force. We will study these forces one by one. Lift force is also included, as well as force due to gravitational acceleration. So let us see the pressure force first. This is given by velocity of the dispersed phase into the pressure gradient. Body force due to gravity is also included, which is nothing but the density into velocity into gravitational acceleration for the dispersed phase. Drag force is calculated by using the drag force equation and the relative velocity between the continuous phase and the secondary phase. CD is the drag coefficient here. Rho c is the density of the continuous phase. d2 is the diameter of the dispersed phase. Now this drag coefficient, various configurations can be used for that, but mostly these type of equations are used for calculating the drag coefficient, which are function of the Reynolds number of the particles. So depending upon the Reynolds number, drag equations are used, different empirical equations are used for the drag coefficient, and the particle Reynolds number is calculated by this particular equation. So this is how the forces are modeled. Apart from these drag force and the gravitational acceleration force, other forces also exist. Lift force exists due to the vorticity or shear through continuous phase flow. And lift force is again given by an equation which is similar to the drag force equation. Cl is the lift force coefficient. Lift coefficient is calculated by various internal configurations. Another force called as virtual mass force is also modeled. This arises because of the fact that dispersed particles, when they accelerate, some part of surrounding continuous fluid also accelerates. This extra acceleration gives an effect of added mass or inertia. So this particular added mass of inertia is modeled by the virtual mass force. That is, the dispersed particles carrying some part of surrounding continuous fluid along with them when they accelerate. It is given by these equations which are internally modeled. Now, after doing all the force balance, velocity field of dispersed particle is calculated. That is, Newton's law of motion is solved. Mass into acceleration is equal to force. We already know the force terms, which are the various forces that we discussed, and also we know the mass of the dispersed particles. So velocities of all the dispersed particles are found out, and a velocity field of the entire dispersed phase is calculated. Once the velocity field is calculated, trajectories can also be calculated by using the definition of velocity of the particles, which is nothing but the time differential of location or distance or displacement. So then the distance or displacement or location is also calculated of the dispersed phase, and in this way track the dispersed particles or dispersed phase. Now within the dispersed phase model, various forces are considered for modeling the interaction between the dispersed particles and the continuous phase. We will discuss the importance and meaning of these forces in detail here. First, let us discuss the particle acceleration. Particle acceleration is force due to the particle acceleration, and it is observed as Newton's second law. That is, the basic acceleration of the particle. Then the drag force is also modeled. Drag force is nothing but the resistance offered by the fluid or in opposition to the particle motion. Pressure force is force due to continuous phase flow pressure gradient. That is, when there is a continuous phase flow, there is a pressure gradient due to that flow or for that flow, and because of this pressure gradient, there is a force that is exerted on the dispersed particles. Virtual mass force, as we already discussed, is because of the additional fluid that is carried by the dispersed phase when it accelerates. This extra acceleration gives the effect of added mass in addition to the inertia of the dispersed phase. This extra mass is modeled by using the virtual mass force. Gravitational force, as we all know, is the force due to gravity. We need to define the magnitude and direction of gravity for considering this particular gravitational force. Then force in rotational reference frames also exist, but they exist only in case there is rotation of the reference frame. This arises only when we have a rotational reference frame or rotational flow. Whenever we have small particles suspended in a gas that has a temperature gradient, these small particles experience a force in the direction opposite to that of the temperature gradient. This particular phenomenon gives rise to a force called as thermophoretic force, which can be modeled using the discrete phase model. Brownian force can also be modeled. This Brownian force arises due to effect of Brownian motion of the micron level or submicron level particles. Safman's lift force is there, which is lift force due to the fluid shear, as we already discussed. Other than these forces, if you want to add any additional force or force mechanism or exchange mechanism, you can use a user defined forces by using the UDF, that is the user defined functions. So all these phenomena of forces that we just discussed can be included in the discrete phase model by selecting various submodels or by giving additional user inputs. Now let us discuss particle injections and what does it mean and what we have to do in order to define a particle injection. Now whenever we use discrete phase model within this commercial software Fluent, the discrete phase is in the form of particles which are tracked by Lagrangian method. The particles of the discrete phase should enter our domain of calculations from somewhere. In order to set their initial conditions and how they enter in our domain, we have to define injections. The particle enter into the domain through the way of injections. Various forms of injections can be defined which are closer to our physical real condition of the physics or problem that we are solving. Various particle injections can be defined which are very close to what exists in reality, how our instrument or equipment work. In order to define injections, we have to define particle position, that is, what is the initial or starting position of the particles, what are its x, y, or z coordinates. We have to define particle velocity. What is the starting velocity of the particle when it enters the domain of calculations? What is its direction? What is its magnitude? We also have to define particle size, that is, diameter for spherical particles. What is the diameter of the particles or discrete phase that is entering into the domain? If we don't have spherical particles or don't have a exact diameter, we may use representative diameters to approximate the physics that we are modeling. We also have to define what is the initial particle temperature. In reality, when there is injection of particles or discrete phase, it is usually in the form of grouped streams of particles rather than individual particles. So in order to define such streams, we have to define the mass flow rate of the particle stream. For transient cases or unsteady problems, we also have to define particle start time and stop time. That is, when the particle starts entering into the domain and when do they stop or where do they stop. Now let us see how these injections are given. There are two ways in which we can specify Lagrangian particle injections. Direct specification of starting conditions, that is, we directly indicate the starting conditions of the particle that is coming into the domain. We manually specify the particle positions, velocity, size, mass flow rate, etc. That is, we directly give the inputs and those values are used in order to define the particle injections or initial conditions. Second option is automated computation of starting conditions. This is suitable for standard equipments like atomizers and other standard injection equipments. Fluent calculates particle parameters based on automation submodels for standard injection devices. For general industrial purpose, various automation techniques are used in standard injection devices that are used in various chemical and mechanical industries. In order to replicate the physics of such injection devices, automation submodels are developed and we can give those automation submodels in order to automatically define the injection device physics. What we need to do is identify which type of injection device that we are trying to model and then select the submodel which is closest to that injection device. First, let us see types of direct specifications. Within direct specification, the first type that we have is single. That is, a single particle enters the domain, we give its velocity, location, position, size, mass flow rate, etc. Second time is group. Within the group particle injection, streams of particles enter. We have to give the starting particle position, size, velocity for the first particle and the last particle, and from those inputs, the entire stream properties are calculated and a group injection is carried out. This is the type of injection that we are talking about. We give the starting particle parameters and the last particle parameters, and all the particles in between. The entire stream is calculated by fluent. Next type is hollow cone, in which particles are injected in conical directions. This is the type of representation of hollow cone type of injection. We will study in detail all the user inputs required for such type of injection in future slides. Next is surface injections, in which particles are injected along the surface, which is this type of injections. Again, we will see all the inputs required for such injection in coming slides. We can also set up a file injection, in which we give the parameters of all the particles within a injection file, which we upload into the fluent calculations. Another type is solid cone type of injection. In solid cone, it randomizes the particles in order to reduce grid dependency. That is, particle parameters are randomized and they can work on any type of grid. Specification of streams is required for such type of solid cone injections, and sufficient number of streams should be specified. Particle properties are randomized. Now, what is meant by this is, it is a truly random distribution of variables. Velocity, direction, and location are distributed in a random manner. That is, any particle stream can have any velocity, direction, or location. It represents a truly random injection in the form of solid cone. Now, when we use automated injections, let us see what inputs we need to specify as users and what parameters are calculated automatically by Fluent. Now, information that users have to specify is location, temperature, starting time, and information about the injector device. Whereas, the size distribution and velocity distribution is calculated by Fluent automatically. That is, which particle will have what size and which particle will have what velocity is automatically calculated by using the various distribution models or automation models. Types of auto injection models that are available are plain orifice atomizer, pressure swirl atomizer, air blast atomizer, flat fan atomizer, and effervescent atomizer. All these submodels we will study in the coming slides. Now let us discuss what modeling features exist within the discrete phase model. What type of features can we model and what type of physics can be included in our modeling problem. As we all know, discrete phase trajectory is solved using Lagrangian approach. We can include the effects of turbulence on the dispersion of particles. We can also include heating and cooling of particles or discrete phase. Vaporization and boiling of liquid droplets can also be included in our modeling. We can also model combusting particles within the DPM model. We can also include coupling of the continuous phase flow field to the discrete phase calculations. We can also model droplet breakup and coalescence. We can also model particle-particle collisions.